The particles of a gas will frequently collide with the walls of the container they are in. Remember that gases consist of particles which spread out and move around in a container in random directions. This means their paths will make them frequently come in contact with the walls of the container. Then these collisions with the walls are what make the particles change direction and bounce around the container. But what other effect will we see from these collisions? Well, the particle exerts a force at right angles to the wall during each collision. We know that in order to change the direction of the particles, the walls need to enact a reaction force on the particles when they come in contact. But this also means that the particles enact a reaction force on the wall because of these collisions. Also, these reaction forces will be at right angles to the surface, in this case the walls of the container. So that's where the individual forces originate from. But what about when we consider all the forces together? The pressure from the gas is the net outward force from all these collisions. Remember that by a pressure we mean a force that's spread out across a surface. So when we consider the millions of particles of gas we'd have in a container, and the forces from all the collisions that would be happening across the walls, this results in an overall force spread across the walls. This is the outward pressure from the gas. For your exams, make sure you can explain what we mean by the pressure from a gas, as well as what causes this pressure. But what property could affect this behaviour of the gas? Increasing the temperature of the gas causes the particles to collide more frequently and with more force. Remember that the temperature of a gas affects the kinetic energy of the particles. In other words, when a gas is at a low temperature, the particles will be slow, while a gas at a high temperature will consist of fast particles. This also means that at a low temperature, the particles won't travel far compared to the fast particles in a given time. So what difference will there be in the forces the particles are enacting on the container? Well, first, since the fast particles travel further in less time, they'll meet the walls more often. So we'll see more collisions happen in the high temperature gas. Also, since there will be a greater change in velocity happening during the collisions, there has to be stronger forces between the particles in the container. In other words, the faster particles cause a greater impact during their collisions. But how would this change the pressure? If the gas is held at a constant volume, then increasing the temperature will increase the pressure the gas exerts. Temperature increases can also cause the volume of a gas to change. You don't need to know the details of this at GCSE, but it's still important that whenever we talk about the relation between the pressure and the temperature, that we specify that the volume is kept constant. So let's look specifically at this steel gas canister. The canister is strong, so its size won't be affected by the gas. In particular, it would inflate or stretch because of this outward pressure. Now let's suppose we heat the gas inside in a way that will increase its temperature, but doesn't cause the gas to chemically react. Then the particles inside will move faster and have more frequent and stronger collisions with the walls. This means that the gas is exerting a greater pressure on the container it's in.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!